Hello everybody, my name is Sergey and I'm here to talk about my project, which is the checkerboard recognition with some built-in piece recognition technology. So I'm going to start by talking about my motivations. I'm going to talk about the experimental setup, and finally I'm going to talk in detail about the implementation of this project. So my motivation is to determine a state of a checker game in real time using a single camera and some machine vision algorithms. I chose checkers because they're sufficiently complex, giving a game tree complexity of up to 2 to a 20, which is about a million distinct games. It's a very well-determined system with very prominent features, namely strong horizontal and vertical lines, which is fairly easy to detect. And it's simpler than chess. I wanted to start at the beginning of the project. I wanted to use chess as the recognition object, but chess happened to be just way too complicated for a semester worth of work on a single camera. So my goals were reliable piece recognition. I would like to make the project fully analytic. I would like to make it transparent, and that is, I would like to see what's happening during every step of the classification process, and I would like to make it real time, preferably at 60 frames per second. I actually didn't quite get there because my camera, unfortunately, was not good enough. So here's my experimental setup. There's Linux host, which is running some OpenCV software written by me in C++. There's a camera, which is pointing directly at the board, which is piping data to that Linux host. And then there's a checkerboard, pretty straightforward. So the big idea here I have is to pretty much run everything in parallel. I have the camera, obviously. A camera is generating frames for the acquisition system. The acquisition system is then sending those frames to the board identification and the piece identification subsystems. The board identification is shown over here, consists of pre-processing, edge detection, and then line detection. And then there's a feedback loop from the line detector into the edge detector to make sure that we're detecting edges of the right precision. Or rather thresholding. And all of these pieces run in parallel along with the piece ID system. So pre-processing is pretty straightforward. I'm only operating on black and white images. So I convert the pictures acquired by my webcam into a black and white picture, and then I low pass filter it to remove some of the high frequency noise. The edge detection is also pretty straightforward. The tool of the trade here is the Canny edge detector. Use a Gaussian filter of k equals 3, and then I compute the gradient along all the points, and I trace along two different thresholds, the T high and T low. T high is used for finding the maxima along the line, and T low is actually used to trace along the line. I found that setting T high to be 10 times T low was sufficient in all cases. And finally we go to the line detector. The purpose, of course, is to take those edges produced by the Canny edge detector and produce real actual lines out of them. And also we expect our lines to be in two main groups, the horizontal lines and the vertical lines. So I throw away any outliers which don't quite match those. And they don't have to be exactly horizontal and vertical, but they have to be statistically significant against all the other lines. But they can be at an angle. So half transform is the tool of the trade here. The minimum line size is about 200 pixels. I use 1 degree accumulator, and I get the picture kind of like this. As you can see, there's a lot of false positives here, and this line over here doesn't really have anything to do with anything. And finally we go to segmentation and classification. This is the work I did from the midterm presentation. This module collects about 10 of the line objects, or 10 frames worth of line objects from the line detector, and then it makes statistical cuts to determine which lines are the best. Then it rotates the board so it's facing perpendicular to the bottom of the screen. In this rotation we also have to rotate the lines, but that's pretty straightforward. It's just a translation and rotation and then another translation back. Then we segment the screen, rather the board, based on where these lines intersect, and then we classify the objects. For classification, I also use another Hopf transform. This time I'm using the circle transform. So I detect circles in each individual square. If I detect circles, I detect a circle, I make sure that its size is at least a quarter of the size of a square, and if that's the case, then I draw a circle over it. And that's about all I have. Next up is the demo. Unfortunately, I won't be able to put audio over it, but thank you very much.